No, no, no hurry. I thought there was a cat trap.
Okay, great. So we're a few minutes after the hour, so I think we can go ahead and get started on our webinar today. So first of all, welcome everyone to another one of our IR Science Interest Group webinars. My name is Meredith McGregor. I will be moderating the webinar today. I am currently an assistant professor at the University of Colorado Boulder, and I'm one of the co-chairs of the IR Science Interest Group. Before I introduce our speaker, I wanted to provide a few brief instructions for how our webinar is going to work today. I've typed these into the chat window as well. Again, you can access that by sort of mousing to the bottom of the Zoom window and clicking on chat, and it will bring up the chat window. So first, we'll start with our talk, and then following the talk, we'll have a Q&A session. The way that will work is please submit questions that you have for our speaker through this same chat window. I will be monitoring this along with Mike Semkoff, the other co-chair of the IR SIG. Once we get to the Q&A period, we will then either read the questions directly to our speaker so that he can answer them, or if you very much want to ask your question directly of the speaker, you can use the raise hand feature in Zoom. That you can find if you go to the participants window. So if you open the participants window, there should be a place where you can say raise hand, and then we can give you the opportunity. I will unmute you and you can ask your question directly of the speaker. You can't unmute yourself. You can also submit questions through the chat window for feedback, comments, questions, or things you want to ask of the Leadership Council of the IR SIG. We will wait until the very end to answer any of those questions. If we don't get to them by the end of the session, you can always still post them and we'll send you an email response afterwards. Please report any technical difficulties you may experience in the chat window so that we can try and address those as well. And finally, this webinar is recorded and will be available to view later on our webinar webpage, which you can find at the link that I provided in the chat window. And I can paste that again at the end. And that's all the instructions for today. So without further ado, I will introduce our speaker for today. Today, we're lucky to have Professor Jamie Bock from Caltech. Jamie has won a number of awards for his work, including the 2016 AAS Joseph Weber Award, the 2018 Gruber Foundation Cosmology Prize, and he's also the PI for SPHEREx, which is what he's going to be talking about today. So the title of his talk will be SPHEREx, an all-sky spectral survey. And with that, I will let Jamie give his talk.
Okay, thanks, Meredith. Yeah, it's a pleasure to be here virtually with the IR SIG. I haven't a lot of experience giving talks by Zoom, so I may not see questions or whatever, but I'll do my best, and please bring them to my attention. Yeah, so I'm going to talk about SPHEREx, and SPHEREx was recently selected for the NASA's next Medium Explorer satellite. These are competed missions. They're small and medium. And we were successful in being selected last February, 2019. As the slide alludes, SPHEREx is going to do 3 targeted science investigations studying the origin of the universe, the origin and history of galaxies, and the origin of water in planetary systems, while conducting the first all-sky near-infrared spectral survey, the first survey of its type, which we think will be very rich for the astronomy community. We think it's a simple and elegant design, and I'll tell you all about it. Here. Okay. When we started developing SPHEREx, we asked ourselves, I mean, we knew this is going to take a lot of effort and time and may not be successful at all. So we wanted to set the bar high. And so in the conception of SPHEREx, there were 3 groups that came together with the most important question they thought in astrophysics, and we put them together because they all combined the capability of near-infrared spectroscopy. And so those questions were, how did the universe begin? how did galaxies begin, and what were the conditions for life outside the solar system. Happily, and it's actually something of an accident, these are themes, the 3 themes in NASA's science plan for astrophysics, and the blue wording says the exact text, but we're investigating basically these 3 questions, obviously not the entirety of the questions, but targeted investigations, which we think are compelling and powerful. Before we get into those, however, I wanted to just give you a little overview of the observatory. SPHEREx is an infrared telescope. At the heart of it is a 20-centimeter telescope, so that's rather small, obviously, but it has a very wide field of view, which is what you want for doing an all-sky survey. Lots of photon collecting power. We tile the focal plane of the telescope with 6 arcsecond pixels, and the spectroscopy is low-resolution spectroscopy with variable resolution, varying between a resolving power, lambda over delta lambda, of 35 up to 130, and covering the near-infrared range from 0.75 to 5 microns. It is cooled in order to get rid of the emission from the telescope and control the dark current on the detectors. And the way we do that, we're in low Earth orbit, as the title slide indicated, and we use entirely passive cooling. So there's basically a 3-stage radiator that radiates the heat out to space, and it has no stored cryogens. When we completed our phase A study, the dimensions of our instrument, it's about 2 meters tall with a mass of about 200 kilograms. And as I said, effective aperture of the telescope about 20 centimeters. Now, things have been changing now that we're in phase B, so we're doing a detailed design study, and so these numbers are bouncing around a bit. But you can see it's a pretty small thing, and in comparison, on the right, you see the shrouds that were provided in the announcement of opportunity, and SPHEREx is this little thing here that sits in the shroud in this configuration with stowed shields. Okay, just a couple words about how the instrument works here. The telescope, as I said, it's a small telescope, but don't let the small size fool you, because it has an enormous field of view. Although the aperture is only 20 centimeters, the field of view 3.5 degrees by 11.3 degrees, and has 6 focal plane arrays, each sporting about 4 million pixels, for a total of 25 million pixels. So for a survey, the figure of merit isn't just the area, it's the area times the field of view, or the étendue, the photon collecting power of the optics. So if we compare, for example, SPHEREx to WISE, you can see here, WISE has a 40-centimeter telescope that has 4 times the area of SPHEREx. However, SPHEREx wins on field of view. We have 65 times more field of view. You can see the WISE field of view here compared to the SPHEREx field of view in green. And actually, we use it twice because we have a dichroic beam splitter in 2 focal planes, one looking in transmission through the dichroic and one looking in reflection. So you get to multiply that field of view really by 2. And so in total, in spite of the small mirror size, SPHEREx has got 16 times more A omega product. And again, that's what you want for covering the whole sky. The cooling system works as follows. Basically, we're copying something similar, which was done with the Planck spacecraft. Planck is a CMB mission with a cooling system that goes all the way down to 100 millikelvin. We're not going that cold. But at the bottom here, between the instrument and the spacecraft, is something called a 3-stage V-groove radiator, which passively radiates heat off into space in stages. Planck's at L2, so doesn't have to worry about the Earth and Sun, which are always on the spacecraft side. And so you can see this 3-stage radiator basically allows thermal radiation to propagate out to space in stages, resulting in a mirror temperature of about 35 Kelvin. Now, SPHEREx is doing the same thing here. you can see we have a 3-stage radiator at the bottom, but because we're in low Earth orbit, we always have the Earth below us, a giant 300 Kelvin black body, and the sun off around 90 degrees to one side. And so while we have access to cold space, we can't let those warm objects shine onto the cold telescope. So we use these things called photon shields that basically don't do a lot in themselves in terms of cooling, but they provide protection from the Earth and sun and the re-radiation of that energy by the shields themselves, while letting the photons from the V-groove radiator bounce out between the shields. So the shields are kind of spread out in angle to allow those photons to escape easily out to space. In fact, the telescope acts as a 4th stage of this cooling system, and then we have something called a focal plane radiator up at the top, which is basically the 5th stage. The focal plane radiator just cools the long wavelength focal plane arrays, which have to be a bit colder to control their dark current. And so we expect to achieve something like 42 Kelvin for the telescope and 30, a little bit colder for the focal plane array. Interestingly enough, these temperatures actually have been achieved in low Earth orbit during the warm phase of the COBE satellite on the Derby instrument. The detectors were actually running this cold. All right, and then the last part of the architecture here is how we carry out spectroscopy. So we had to come up with an unconventional way to do spectroscopy. And that's because if we look at our optical system, if we built a conventional spectrometer with our optics, we would need something like 6 of them to cover the band of interest. And each one would be roughly the size of the telescope. So a conventional spectrometer would just be enormous and wouldn't be feasible. So instead, we hit upon an idea, which is to use something called a linear variable filter or a ramp filter. And basically, it's an interference filter where the central wavelength varies linearly along the filter. But the interference layers themselves provide a defined passband. And you can choose these in the design of the filter. We purchased one of these filters, and you can see here the design progression in wavelength versus what we measured, and they lie right on top of each other. So the filter itself works really well. And then we place these filters right on top of the detectors. So each pixel on the detector is looking at a somewhat different wavelength. And this is what the focal plane assembly looks like in design with the filters placed over the detectors. And then, as I mentioned, there's actually 2 focal plane assemblies, each with 3 arrays and 3 LVF filters, and 6 in total, 2 in transmission and 2 in reflection. This shows a prototype of the assembly here with sapphire blanks. That's the substrate of the filter over mechanically and thermally representative focal plane assembly. So the way this works is to get the spectrum of a source, we take a series of images. Okay, so basically to get a complete spectrum, we have to take 48 exposures, which results in 96 spectral measurements. Now this would be horribly inefficient if we were interested only in the spectrum of a single source. And that's why astronomers don't do this. They put all their pixels on the source of interest. However, our source of interest is the full sky. So while a single source requires 48 exposures to get a complete spectrum, the other pixels that aren't looking at the source are looking at the sky, and they're also taking spectra of the sky. And so basically, in this configuration, we're mapping the sky very efficiently. And it took a while for us to figure this out, that this was a very efficient way to do it. The filters themselves are basically just pieces of sapphire. They weigh a few grams each, so that's a very space efficient way to do this. After coming up with this idea, we found out that planetary astronomers have known about this for a long time and actually have flown them. In fact, the New Horizons spacecraft, which is now past Pluto, incorporates LBFs in this configuration placed over the detectors and made multi-wavelength maps of Jupiter and Pluto and other objects. And there's another planetary spacecraft called SPHEREx, which is doing much the same thing. Okay, so when we want to carry out our all-sky survey, then what we need to do is we need to take a series of exposures that covers the whole sky. And so here's how that works. SPHEREx here is in low Earth orbit, and we're in a polar orbit. So basically going over the north and south poles along the sunrise-sunset line, or the terminator line. So here's SPHEREx. Again, the Earth is below us, 90 degrees below us, and the sun's off to one side. And we're basically looking up at the sky 90 degrees from the sun. Obviously, we're not the size of Switzerland here. That's something of an exaggeration, but we go around the Earth like that, and we have to always maintain avoidance to the sun and to the Earth. So we have avoidance criteria. We always keep the sun 90 degrees off axis, and we always keep the Earth well off axis. So that means we can look within a cone of about 35 degrees from local zenith. So then to observe the entire sky, what we do is, here are those avoidance regions. You can see the plane here is the 90-degree rule for the sun. The green cone is our avoidance to the Earth. And we want to sit here and stare at a region to build up sensitivity to do spectroscopy. Each integration is about 100 seconds. And so we sit there and point, but as we're pointing, the orbit is taking us around the Earth. And so the Earth is coming up and eventually will get too high. And so we have to slew away to avoid the Earth. So what we do is we take a series of exposures, and you can see each exposure is followed by a small step. We take another exposure, and we do this as long as we can until the Earth comes up again, and then we execute a large slew to maintain our avoidance criteria. So there you go, there's a large slew. That puts the next observing region at the end of the cone, and then we continue this process of doing the stepped small slews, exposure followed by a slight motion, followed by another exposure. So over the course of 6 months, we have access to the full sky, and we can provide a complete coverage. So this is what our coverage looks like after 1 month. We're basically observing roughly along a great circle that's 90 degrees from the sun, approximately. And in a month, we've built up observations around this great circle. And you can see here the blue is where we've got at least one observation, and some places we're getting additional coverage. And then so on after 2 months and 3 months, and after 6 months, well, this is 7 months, we've covered the full sky and started on the next survey. You can see this strip starting here again where we built up 2 observations. And finally, 13 months now, we've completed 2 surveys and working on the 3rd survey. And over the full proposed mission, we've completed all 4 surveys this way. We're still studying. This is, by the way, I should say, this is an early realization of how the survey works. This is getting more and more sophisticated and refined. It also provides the opportunity, all of these great circles cross here roughly at the ecliptic poles. So the poles provide an opportunity to have deeper coverage. And in fact, we take advantage of that by having deep fields to do unique science at the north ecliptic pole and near the south ecliptic pole. Okay, so let's go back to our science questions and see how SPHEREx addresses them. So our first question was, how did the universe begin? Current cosmology theory, the current paradigm says the universe actually began in a period of exponential growth called inflation, something like 10 to the minus 32 seconds after the Big Bang, or maybe it was the Big Bang. inflation was invented by theorists in the 1980s to explain the flatness and homogeneity of the universe, and has done a good job of doing that. But the physics that drive inflation are not well known. What SPHEREx contributes is we are observing a particular observable of inflation, which has to do with a parameter called non-Gaussianity. It has to do with the statistics of fluctuations, the initial fluctuations set up by inflation. And depending on the physics of inflation, in particular, whether it was driven by a single field or multiple fields, non-Gaussianity is a probe of that. Now, non-Gaussianity has been probed with Planck most recently in the statistics of the fluctuations of the cosmic microwave background. But the microwave background here is really a two-dimensional surface, and there's a finite amount of information in this surface. Planck has measured that nearly to cosmological noise limits. And so further improvements in our measurements of non-Gaussianity aren't going to get a lot better from the microwave background. But the fluctuations from the microwave background grow into large-scale structure that's traced out by galaxies. And SPHEREx will create a three-dimensional picture of these fluctuations using the redshift and position of galaxies in the more recent universe. And that three-dimensional picture has more cosmological information, and therefore, in the case of non-Gaussianity, allows us to do roughly 10 times better than Planck did. So as I mentioned, the idea of inflation is that the universe went through a period of rapid exponential growth. And this is a figure from Alan Guth's book. And you can see this red region is the entire observable universe that we can see with photons, just this little bit here at the end. And inflation says at this very early time, the universe went through an exponential growth, and that exponential expansion drove the geometry of the universe close to flatness. And we now know the universe is very close to flat indeed. It diluted the abundance of magnetic monopoles, and it provides a homogeneous universe, which we observe. The quantum fluctuations at this early time were blown up to macroscopic sizes by inflation. And so the fluctuations we observe in the microwave background and in galaxies started as these quantum fluctuations. At this very early time, the energy scale of the universe is getting hotter. It's way beyond the energies of that we explore through the standard model of particle physics. So perhaps inflation has something to do with grand unified theories, but it's way beyond the energies we can directly access from terrestrial particle accelerators. So to understand the physics of inflation here, perhaps for the short term, our best observable will be the universe itself. So since the theory of inflation came forth in the 80s, there have been several generations of increasingly precise measurements of particularly the cosmic microwave background, culminating in these exquisite measurements from Planck. And the microwave background is in violent agreement with the basic tenets of inflation. All these predictions made in the 80s have now been verified by these precise measurements of the microwave background, in particular that the universe is geometrically flat, and the fluctuations have a nearly scale invariant spectrum, but not quite as predicted by inflation. And the fluctuations in particular have nearly Gaussian statistics. But depending on the model of inflation, we expect that there may be a deviation from that. What non-Gaussianity means, one way to think of it is you can simply take this distribution of hot spots and cold spots and look at the histogram. Now this might not be, it isn't, the most statistically powerful test, but it basically explains the idea. And depending on the model of inflation, we expect a deviation from a Gaussian shape parameterized by something called FNL, which is the non-local, nonlinear non-Gaussianity term. And to date, that we have no detections of it, but SPHEREx will use large-scale structure to improve these measurements by an order of magnitude. So to probe inflation, we want to look, use a universe as an observable. And there are basically two observables currently that are within our grasp experimentally. And that's to look for a background of inflationary gravitational waves through the microwave background and polarization, or to search for non-Gaussianity. And these are two independent probes of the physics of inflation and probe different properties. So particular inflationary gravitational waves, if inflation is driven by a single field, this tells us the energy scale of inflation. Non-Gaussianity is really sensitive to multiple fields, and so that'll tell us whether the inflaton field was single or multi-field. Question. Oops, I guess we can save that to the end because we've gotten so far past it at this point, sorry. Okay, so here's the limits on non-Gaussianity today. CMB is saying FNL is less than a value of about 10, and it's pretty close to the cosmological noise limit. Large-scale structure can do a better job, and this is an exaggerated graph showing the fluctuations traced in large-scale structure for extreme values, for illustration, of FNL. And the idea here is that the galaxies trace out the underlying dark matter field, which is coming to us from initially set up by inflation. And by using the statistics of these galaxies, in particular, the distribution of galaxy pairs, called the power spectrum, or a two-point function, or galaxy triples, these triangles, which is the bispectrum, or a three-point function. The distribution of these can serve as a powerful probe of non-Gaussianity. But as perhaps hinted at by these pictures, the signature of non-Gaussianity really comes about from large spatial scales. So one needs a large survey, or ideally the entire sky, to search for this. Okay, so what SPHEREx does is we take redshifts of galaxies, basically using this low spectroscopy information that we have. And in particular, because we have to have somewhat large pixels, 6 arcsecond pixels, we're taking sources from prior catalogs with known positions. So that controls issues like blending and confusion. And from those known positions, we extract the spectra at that position. And we fit these with a template library to get the galaxy redshift type and an estimate of the redshift error. Here's two examples shown in the graph. One is a galaxy at a redshift of about 1/2 here. It's passive, and you can see the strongest feature really here is this 1.6 micron bump, which is a feature from older stars. And so that's providing the redshift for this galaxy and its type. But this is a broad feature, so the redshift accuracy is not so good. It's limited by the width of the bump here. A second example is a galaxy at higher redshift without a prominent bump, but with line emission from H alpha and H beta in particular, and a bit of a break coming in here, 4,000 angstrom break just starting to come into our passband. And the lines for this particular galaxy would give a higher redshift accuracy, as it turns out. So we take our galaxies and we break them up into accuracy bins, and we project that we'll have something like 450 million galaxies or more with an redshift accuracy of 10%, and then a smaller population of high accuracy redshifts, something like 0.3% accuracy, 10 million galaxies. And the higher accuracy galaxies generally are brighter ones and therefore at lower redshifts. This is a little bit of a visualization for what that sample of galaxies looks like. So here we are doing a fly-through through a simulated data set. This is just a small fraction of the galaxies. So we're flying through in redshift here, and each of the galaxies you see going by, we get a type and a redshift for. And the galaxies are tracing out the underlying dark matter field, which is shown in blue. Obviously, we're measuring the galaxies and inferring the dark matter field. And as we're going out here in redshift, you might notice now that the number of galaxies, the density of galaxies, seems to be falling off. And that's a result of the selection function of the instrument. As galaxies get further away, they get harder to detect. So our galaxy redshifts go out to a redshift of 2, but you can start to see here at a redshift of 1 this reduction. But nevertheless, we get a lot of galaxies. And the end result is that we can use both populations of galaxies, these low accuracy populations and the high accuracy populations, to constrain non-Gaussianity. This graph here shows the current accuracy on non-Gaussianity. So non-Gaussianity now is on the x-axis. And the large blue ellipse is what is currently allowed from the Planck measurements. The non-Gaussianity could be anywhere in this ellipse. The y-axis is the running of the spectral index. So that's the curvature in the index of initial fluctuations. Again, that's another measure of inflation, and it's also not very well constrained. When Euclid comes along with a power spectrum measurement, that will do a good job on the running of the spectral index, and so you can see the smaller ellipse provided by Euclid. SPHEREx will use the power spectrum with the low accuracy galaxies in pairs, and the bispectrum with the higher accuracy population in triples. And you can see here these ellipses. We don't know where these ellipses are going to fall, but you can see these two ellipses and their combination is quite small. Now, inflation could be driven by a single field, but a single field inflation predicts negligibly small levels of non-Gaussianity. So all these single field inflation models, the one you read about in Coleman-Turner, they all lie along this single line, okay? And multi-field models will, however, generally predict FNL of order 1 or so. And so we wanted to get an accuracy that exceeds FNL of order 1. Even non-inflationary models predict something of order 1 FNL. And so this blue kind of shaded region shows artistic distribution of these multi-field models. So if the ellipses landed here, this would actually be an important finding. It would say that we could rule out single field inflation if that was where the measurements landed, and that inflation must be driven by multi-fields. So our target sensitivity here is to have a sensitivity to non-Gaussianity of less than half at 1 sigma FNL. Our second theme is how did galaxies begin? So this is the same cone, the evolution of the universe, except now instead of showing large-scale structure, the cone shows the history of galaxy formation, starting from the first stars, which ended the cosmic dark ages. These are the initial stars formed out of primordial hydrogen, turned on, and then the first galaxies, and eventually this shows the process of reionization. The UV photons from these initial objects ionize the surrounding intergalactic medium, which is neutral hydrogen that's been neutral ever since the time of the microwave background. Galaxy formation continues on apace. We know from studies at multiple wavelengths that star formation in galaxies appears to have peaked about 5 billion years ago, a period called cosmic noon, and has been on a slow decrease ever since. There's also today evidence for some amount of stars in the fuzzy peripheries of galaxies called interhalo light. And so with SPHEREx, obviously, we're not going to measure these individual objects off at very high distances at the epoch of reionization. That's a job for JWST. We're going to use our large collecting throughput to measure the extragalactic background light itself. And this extragalactic background light is the integral of all the photon emission over cosmic history produced by galaxies. Now, there's a problem doing this in absolute brightness because of local foreground. So this picture shows the problem with absolute photometry. On the left here, you see the plane of the galaxy. That's a pain. But the real problem, or a more serious problem, is this glow out here, just past sunset. Actually, what you're seeing is scattered light from the dust in our solar system, so-called zodiacal light, which reflects sunlight strongly out in the optical and then re-emits in the infrared. And so the zodiacal light is many times brighter than models of the extragalactic background. And so this is very difficult to do. A new method is to study the fluctuations themselves as a tracer. And this basically relies on the fact that the zodiacal light is very spatially smooth. And furthermore, it varies over the course of a year. So we can use this fact to use basically the anisotropy, the fluctuations from galaxies themselves, as a tracer of the total background light. So what you see here, this is a numerical simulation of dark matter. And galaxies trace this dark matter distribution. On large scales, before the nonlinear effects of gravity have come into play, this linear clustering regime is basically a proportional tracer of the total light production at any given epoch. And so as galaxies trace out this field, this spatial distribution is a tracer of the total light production. So basically, it's a way of getting at the extragalactic background without measuring the total glow. These kinds of measurements have been done fairly recently. So this is a picture that I like to show, which is a map made in the far infrared by Herschel Speyer. And it's a 3-color map. And you see a few discrete objects here. These are actually lens galaxies. But the overall quilted pattern doesn't necessarily resolve into individual objects, but that quilted pattern is this linear clustering of galaxies. The problem here in the far infrared in 3 colors is that we measure these fluctuations exquisitely well, but modeling how they happened in redshift is difficult because all the emission piles up into the far infrared, and it's hard to disambiguate different redshift histories. In the near infrared, there's current controversy. Fluctuations have also been measured in broad bands with Spitzer, with Akari, a Japanese satellite, and Cyber, a rocket experiment. And fluctuations are detected, and there's a debate about what they're coming from. One group by Sasha Koslinsky thinks that their signature of first stars at high redshifts. A more mundane explanation is that a component is coming from stars stripped in gravitational interactions at low redshifts. And so this is known in clusters. This is a measurement of so-called interhalo light from stripped stars in a cluster. Question is if this is happening in lower mass systems. And the key to disambiguating scenarios like this is really doing this redshift separation. And in order to separate the redshift histories, multi-wavelength measurements are key. So the way this works is, this is a little illustration. Here's a dark matter map, again, from a simulation. And if I took a large telescope and measured the galaxies independently, like this, I would see the brightest galaxies, which are set by the sensitivity of my telescope. And at the end of the day, I would be left with those objects. And I could follow them up and determine their redshifts and what's going on in them. Independently, though, I can do this mapping measurement. And so everything in the map is what I measure. I don't measure necessarily as deep on individual objects, but I measure the emission from everything that's in the map. And the beauty of that is that I'm sensitive to all emission sources. I'm sensitive to emission from galaxies and the galaxies that I know about in particular. But I'm also able to measure emission equally well from objects that might be individually too faint to detect, such as dwarf galaxies, which we think are responsible for reionization, these diffuse emission components like strip stars, and any exotic scenarios. So these two methods are very complementary. And again, the key to getting this redshift history is really spectroscopy, to break apart components using their unique spectral signatures. And in particular, the reionization process should have the distinct spectral signatures from basically hydrogen itself. And so that's the idea. And SPHEREx will do these measurements in the deep fields at the ecliptic poles, where we're going to have deep, redundant observations with all the kinds of map-making jackknives and so forth one needs to do these very sensitive mapping measurements. And then they get broken into 96 channels, and we can use the spectral information to provide a separation. We can look, by the way, not only for continuum features, such as these two scenarios from first stars or interhalo lights, but we can also use the multi-wavelength observation to look for line features. And strong emission lines like H alpha and H beta, we should be able to trace out those lines, basically use the lines to do tomography in the third dimension to trace the line emission. And with H alpha, and we should be able to go from a redshift of about 0 out to a redshift of 5. And potentially at higher redshifts, we could also do Lyman alpha. So there's many things you can do with these maps. And then finally, moving on to our third theme, the question we wanted to address is what are the conditions for life outside the solar system? Today, we only have one data point, the conditions for life in our own solar system. And on Earth, the abundance of life is apparently very closely tied with the abundance of liquid water. Where did that water come from? We think that the water that on the Earth, in the Earth's oceans, actually had an interstellar origin, that in the history of our solar system's formation, ices were brought to the Earth from asteroids or comets or other objects. We're not quite sure. There's a current debate going on about that. But those interplanetary ices in these forms then furthermore had an interstellar origin. They began as interstellar ices, which we know exist. Basically, these are ices that form on interstellar dust grains. And in particular, water ice is prominently formed on interstellar dust grains. If one were to ask for young star-forming systems in dense molecular clouds, so in dense molecular clouds, where is the most of the water? It's all in the form of ices on interstellar dust grains. It's not just water ice. There's carbon dioxide, carbon monoxide, methanol ice. So these interstellar ices not only are important for ingredients of life with water, they also have organic materials, and those may have also been important for life on Earth. So we know the signature of interstellar ices thanks to previous infrared spectral measurements, but only in something like 100 or 200 sources. SPHEREx will measure the abundance of ices through absorption spectroscopy over the entire sky, and we'll trace those abundances from native clouds into young systems and understand how the ices are processed from their interstellar origin into interplanetary ices. So this is basically how this works. What you see here is a spectrum of absorption spectroscopy from these solid state ice features. And the features are particularly rich here in the 3 to 5 micron regime. You can see the very broad absorption feature from water ice, and then weaker features from methanol, and then features here from carbon dioxide, carbon monoxide, and an XCN stretch. And SPHEREx will use absorption spectroscopy to look at these fingerprints as they evolve from dense clouds and then through the early stages of the star formation process, from young stars to stars that have protoplanetary disks, to the few systems we know about that appear to be going through something like the late bombardment phase that happened in our own solar system. And our goal here is to measure ices with high signal to noise in at least 20,000 systems. But if SPHEREx works at all, we should get something easily above 1 million sources. So it's going to be very rich. These will be predominantly in the plane of the galaxy, but of course, we'll be measuring the full sky. And I think it'll really be a game changer for these studies. Finally, SPHEREx, in the process of these 3 science themes, will create an all-sky legacy archive, a spectral survey at 6 arcsecond pixel resolution over the full sky, really the first data product of its kind. And this is going to be very rich. I mentioned the number of galaxies, and so there'll be hundreds of millions of galaxies with medium accuracy spectra and tens of millions with high accuracy spectra. In addition, we'll have spectra of galaxies in 100,000 clusters. So anything involving galaxies, especially with statistics, is going to be very, very interesting. For stars, we'll also have quite a collection of spectra for stars, and going down to some dwarf stars. And then there will, in addition, be possibly some surprises. For example, quasars at high redshift. We know now there are 3 quasars at redshifts higher than 7. They really pop out in the SPHEREx data set because of the wavelength cut in the infrared. And we don't know how many of these will appear, but they'll be lurking in our data. SPHEREx will also do interesting things on the abundance of and spectra of objects in our solar system, and allows things like making line maps, emission maps over our galaxy. You can see here the approximate depth of SPHEREx. It's roughly an AB magnitude on the all-sky survey of about 19 AB mag. Each of these points represents an independent measurement. So there's 96 of these points, and that's 5 sigma sensitivity of about 19. There's a little bit of a range here, depending how well the instrument works. At the long wavelength bands, the sensitivity falls off a bit because the spectral resolution is higher in order to do ice science. So individual sensitivity per band is a little bit worse, but of course there are more bands. In the deep field, things get better. This is only showing the statistical sensitivity. It doesn't include the effects of confusion, but you can see statistical sensitivity is about 21st AB mag. And so this is nicely complementary to 2-mass, for example. Every 2-mass source ought to have a reasonable spectrum. The WISE sources detected in photometry will typically have about a similar sensitivity per channel with SPHEREx. And then at short wavelengths, all-sky surveys such as pan-stars, there'll certainly be objects in pan-stars that we don't see with spectra, but these points tied with infrared measurements are the basis of our cosmology catalog. We're always looking for community participation with SPHEREx, and we've had a series of of workshops. And when I say workshop, I really do mean workshop. We asked people to come and share their ideas with SPHEREx and how we with SPHEREx could facilitate those. And so we've actually had a series of these about every 2 years now. We've had our first one in 2016 was at Caltech. And the picture here is in February at CFA in Cambridge. And most recently, we had a workshop early this year in New York City at CCA. And each one of these workshops is focused around a theme. And, you know, it is a workshop, so we do ask people to come in and present ideas instead of their usual thing. The 2016 workshop, for example, we asked for ideas for using the SPHEREx survey and how with SPHEREx we could facilitate those with the way we produce our data and deliver data products. And actually some new ideas came out of this workshop that we hadn't thought of. And I'll just name two of them. One was that the masses and radii of exoplanets, the uncertainties are actually in many cases driven by the properties of their host star. And SPHEREx, providing a spectra combined with Gaia, can actually improve these errors quite significantly. And so this has resulted in us endeavoring to deliver a catalog of spectra of host stars to facilitate more accurate measurements of the exoplanet properties. Another theme that arose is the many synergies between X-ray surveys, in particular eROSITA, the many hundreds of thousands of X-ray sources determining their redshifts and properties are a natural synergy with SPHEREx. The 2018 workshop focused on synergies with other NASA missions, and then the 2020 workshop has been focused on collaborative opportunities with the survey data. And so we plan to continue doing these and hope to, you know, get further participation and new ideas. So that's it. I just wanted to recognize for my final slide the invaluable contributions of our science team. And, you know, we're very glad to be in phase B, and we're in the process of going through a detailed design phase right now in phase B, and looking forward to building hardware and getting up into space. So thank you very much. I'll be happy to take questions.
Great. Thanks, Jamie, for a really wonderful talk. We already have one question into the chat window, so we'll start there. But I just want to remind everybody that if you have questions, please type them into this chat window, and then I will read them to our speaker. If you very much prefer to ask your question directly to the speaker, you can also use the raise hand function that can be found in the participants window. You can click on raise hands, and then I can unmute you and you can ask your question. But let's start with this question, which I think was earlier in your talk, which says that I noticed on a previous slide that it would take 6 months to get a complete spectra. If you were looking at multiple targets during the same period of time, due to the Earth getting in the way of the targets as SPHEREx orbits, how many targets can you get spectra on during this 6-month period?
Okay, well, let's see. The way the survey works is every 6 months we get a spectra of the full sky. So any object will get one complete spectra during those 6 months. Now, when that happens depends where the object is and what, you know, the properties of our orbit and so forth. But you know, this survey animation kind of shows that if your object was in this blue stripe, it would have had a spectrum taken in the first month, and so you have a complete spectrum at that point. So N hits here means complete spectra, and then after 6 months, it doesn't matter where the object is, you'd have a complete spectrum. And over the full mission, you should get at least 4 complete spectra.
Another question, which I think is asking for more details on the schedule for phase C and D and E. I think the general schedule for the mission forward from now.
Right. Well, as you can imagine, things are a little unpredictable at the moment with the COVID situation. So we are planning to go through our preliminary design review and key decision point C, which is the transition from our design phase B into hardware, which is phase C. So at this point, we're shooting for that happening in the fall of this year, TBD, right? Everything keeps moving around. And one of the important things is going into phase C, for example, we need to have schedules from vendors. And so since the COVID situation, that's been difficult to pin down. But on the other hand, we've been able to make really good progress on the designs because that all can happen from home. Phase E will occur when we get into launch. That is officially happening still in late 2023, but I think given what's happened this year, it's probably going to move into 2024.
Okay, another question is what is the contribution of all sky surveys versus deep survey to the FNL measurements, in parentheses, given the presence of the Milky Way in the all sky survey?
Yes, so our all sky survey is only what we've assumed for constraining FNL. The deep survey might offer some additional information there, but we haven't assumed that we use it. Furthermore, we've cut out 25% of the sky due to the galaxy in our calculations for FNL.
And this is, I think, a comment that says, please note that the time required to obtain a spectrum for a given source is a few days, not 6 months. Spectra for all sources takes 6 months.
Yeah, this is just getting to this point here. Again, like if your source were in this blue strip, you get a complete spectrum. To get that complete spectrum, it'll take multiple orbits to get 48 exposures. And you know, it varies a bit where you are on this stripe, how long that takes. But typically, as Gary's saying here, it's a few days if your object fortunately lands in this blue strip to get that complete spectrum. And then that strip of observation moves around as time goes by. Hope that's clear.
Question.
Why not a bigger telescope? Yeah, well, you know, the simple answer is that, you know, for an explorer, the first order of business is to fit in the box, to fit in the parameters of an explorer. And if the mass, the size of the telescope kind of drives the whole design and the whole cost. So it's expensive. A somewhat more nuanced answer is that a bigger telescope allows smaller pixels, great, but that means it takes more exposures to cover the sky. And so that means you need, you have less time per exposure to integrate. And we're doing spectroscopy, so we need time to get sensitivity, right? We're only looking in a narrow band. So a larger telescope with smaller pixels means that you don't win as fast as you might think because of that effect, assuming you're going to cover the whole sky. Furthermore, the optics here are quite fast. It's f3 at the focal plane. So if you made a telescope with the same pixel size, it's difficult to actually support the same field of view because the optics get extremely fast as you make the telescope larger. So we did think about that, and you know, it's bigger is always better, but it's not better by as much as you might originally think.
Great. Another question is, how will data releases work? Will they be yearly or continuous?
Yes. So the answer is yes. We will have, first of all, basically continuous releases of what we call the spectral images. And so spectral images is basically the image as recorded by the instrument with the wavelength varying over the image. And calibrated versions of those images will be released within a couple months of when the data are taken. Just time for us to do the calibration and flagging and that sort of thing. And those spectral images are really the currency of the data library. If you want to take the spectrum of anything, the best way to do it is to go back to the spectral images and extract the spectrum at your chosen positions. And so those will be available, pretty much immediately. At the completion of each survey, which is about 6 months, we will go back and recalibrate all those spectral images from the past and going forward. So there'll be recalibrations at the end of every spectral survey. And we will also provide, after the end of survey 3, what we call high reliability source catalog. So these are, it's just a catalog of objects detected robustly that will come out. And then finally, at the end of the mission, we'll provide the galaxy catalogs and the deep sky maps, as well as 3 legacy catalogs, which will contain spectra for exoplanet host stars, low mass stars, solar system objects, and galaxy clusters. So those are intended to be user-friendly catalogs. You don't have to go back to the spectral images to access that. And also, we intend to provide tools for the community to go off and collect photometry on any given point of the sky, as well as some visualization tools to explore the data.
Okay, and another question is, for a passive galaxy, is there available data that shows the 1.6 micron bump can support a 10% accuracy of photo Z?
Well, I can only explain, I guess, there's not data per se, I'm not quite sure what you mean, but what we've done is we have simulated all of our observations. So I don't have a good slide of this. I'm trying to find the spectra. Okay, so what we did is we took data from the Cosmos survey field and all the galaxies and spectra in that field. And that's quite deep. It's much deeper than we will get with SPHEREx. And we took these prior sources, prior positional information from optical measurements. And then we simulated our observations with SPHEREx, fit these to templates that are different from the templates used to create the spectra of the objects themselves, and estimated the redshift accuracy compared to the truth that's in the catalog. So we simulated this whole process end to end. And these histograms of the accuracy are compared to the truth that went into the simulation. So I would say we don't, there is a paper that we have on this process that you can read about more, but yeah, it's definitely based in data to show that we can get this kind of accuracy.
And a comment that says, regarding the bigger telescope, you don't need to aim for diffraction limited resolution, but you can collect more photons faster for spectroscopy.
Yes, that's right. And we're not diffraction limited for most of our bands as it is with 6 arcsecond pixels. And yes, you can collect more photons if you can maintain the same field of view. But as I said, we're already at a focal ratio of 3, and the optical system doesn't work at a focal ratio of 2, which would, which is what you need to do to preserve the same field of view. So you do get a bigger field of view. So what you need to do is pack in more detector arrays to really get an advantage. So it is possible to get an advantage, and but it costs money. And as I was alluding, it also takes more images, and so you don't win as quickly as you might think.
Great. So please feel free to continue typing in questions for our speaker. I just want to provide a few wrap-up words since we're after the hour, and thank all of you for joining us for another one of our webinars. We hold these webinars generally the first Tuesday of every month at the same time, 1 p.m. Eastern, 10 a.m. Pacific. So you can join us again in July and in future months. And lastly, if you're interested in speaking yourself at a future webinar, or you want to nominate someone as a speaker, please contact any of us on the IRSIG Leadership Council. We especially invite suggestions for early career scientists of diverse backgrounds. And I'm happy to stay on, and I'm sure Jamie can stay on for a little bit if there are additional questions you want to ask. But otherwise, thank you so much for joining us.
Yeah, I'll hang on for a minute or two in case there are further questions. Mike, where's the beard?
Oh, that's young me.
Oh, okay. That's just a picture.
Yeah.
Okay, I think people are